welcome back. I would like to thank our next presenter, Alexander Ursoy, for joining us today. He is also a team member and a senior leader in Health and Life Sciences Cloud and Data, working on our capabilities in medical imaging and DICOM. That is our next session here at the intermediate level. And Alexander, we'll turn it over to you to talk about our capabilities, what's upcoming, and some use cases. Thank you so much, Alexander.
Thank you so much, Dana. And it's great to be here again. Welcome everyone to our sessions. We will specifically focus on the medical imaging and DICOM capabilities that we have within Azure Healthcare APIs. I would like to start with a brief introduction. So this is me, Alexander Mehmet Ersoy. I have joined Microsoft almost a year ago. I've been working in Azure Healthcare APIs team and responsible for as a program manager responsible for the DICOM service that I work closely with Stephen Borg. You may have been in touch with him. And I have been in the medical device field since 2010. I worked on various roles such as a development engineer, MPI lead, as well as program manager. Started with imaging modalities, and then I got into patient monitoring devices, as well as some image chain component products. And then I worked on innovation and strategy management for medical devices within Philips Medical Systems. From there, I'm sure you're familiar with the outline of the training week that you guys go through this week. We are in the medical imaging and DICOM. And as you have probably already heard, I will repeat it very quickly that data really sits in the center of our Microsoft Cloud for Health. And of course, imaging data is part of the healthcare data, which has a lot of intersection with rest of the medical data that a patient can have, but it is also the area which has the most silos in the field that unfortunately most of the imaging data is not connected with each other, and as well as is not connected with the clinical data of patient. And in today's training, we would like to go through how we can onboard it into cloud and how we can connect the imaging data with the rest of the imaging data as well as with the rest of the patient data. So from here, before we dive into the capabilities that we have in Azure Healthcare APIs, I would like to give you a brief overview if you are new in this area, especially what is DICOM and how it is transmitted. So when we say DICOM actually it's known as Digital Imaging and Communications in Medicine. It is the international standard for medical images and imaging format and related information. And in DICOM standard, images are stored and transmitted between devices, such as like modalities, picture archival and communication systems, and as well as vendor neutral archives and more. And DICOM really brings the easiness into that storage and transaction of the data in structured format. And DICOM data also referred as a DICOM object, because when we look at DICOM data, we will also get into that we have imaging data and the binary text data. It can be also referred as a DICOM object as an overall umbrella and contains two types of data. So here in this example, we are seeing a DICOM object. The left-hand side is the imaging data, which is created during the image acquisition operation in a CT scanner or any modality you can think of, such as ultrasound, MRI, and so on. And on the right-hand side, you are seeing the DICOM tags. Of course, this is not the full list of DICOM tags that are available in a DICOM object. Okay, I thought there was a question, but this is just a small snapshot of what are the DICOM metadata that you can see in a DICOM object. And metadata organized is a constant and standard series of tags that are defined part of the DICOM standard. And of course, you can also add additional tags with our service that helps you to index your data much more effectively. But we definitely provide minimum set of, we definitely store the defined set of DICOM tags that are defined by the DICOM standards. And by extracting the data from those tags, one can access the important information regarding to patient demographics, study parameters, and so on. And imaging data is a pixel data that makes the image. And as we are familiar with the DICOM object, I also would like to make sure that we are aware of the DICOM data model levels that we can see. Of course, at the top we have the patient, but as a patient, I can have multiple studies. For example, I might have taken a cardiac CT scan a month ago. It will be registered as a study itself, and another month I have another imaging study done on me. It will be registered as a different study, and in one study you can have multiple series. For example, while my cardiac CT scan is being taken, they can be taking some survey scans, and after that they will repeat a cardiac CT scan. Each will come as its own series, and a study can have multiple series. And also in one series, for example, in cardiac CT scan, you will have multiple images that make that series. You can have like as minimum as one image in a series, or you can have 50 or 100 images, depending on the resolution of the and slicing of the scanning that has been performed on you. That number may change. And of course, also the other thing that I would like to bring up that as image sizes increases on a series, that will definitely increase the size of your image, size of your study on a given patient. And as we talked about what is DICOM object, what are the different levels or hierarchy in the DICOM levels, I also would like to say that DICOM standard is not only used to store the image in a given modality or on a given archival system, but also DICOM standard is being used to transfer DICOM object between entities. So from a Contosa hospital, your DICOM image can be transmitted to your payer or another academic research center to get a second opinion. And the way that DICOM objects are transmitted across the entities, it can be done with DICOM Web. But DICOM ensures that it's a closed system to perform certain transactions such as store, display, query, retrieve, print, as well as managing the workflow. For example, DICOM images ensures that structured documents can be exchanged for research care management and billing purposes between entities as shown in the diagram. And how it is being transmitted. So DICOM Web is the DICOM standard for web-based medical imaging, and our DICOM service is only compliant with the DICOM Web standard. It is the family of the RESTful DICOM services for sending, retrieving, and querying for medical images and related information. And as you can see, the certain services or transactions that we support are the like query, retrieve, store, work list. It's also another capability that we are actively working on to enable in our services. And also I would like to say that only 5% of the DICOM assets are in DICOM Web, but that percent of adoption is exponentially increasing as a lot of institutions, research centers, and as well as private clinics are merging into cloud for easy access of the images. Because until recently, not too far along, DICOM has been a modality that principally lived in the data center. For example, in a hospital, there was a CT scanner, and once CT scan gets done for a patient, the image was pushed into picture archival and communication system, PACS system, so that in PACS system, the radiologist can view the image, write the report, And then once that image gets out of the clinical workflow cycle, it was being pushed into VNA in the given hospital, which is the vendor neutral archive systems, which keeps the image for the longer archival purposes. But recently now, with the DICOM web, there is a big push from PACS VNAs to cloud-based picture archival solutions for DICOM. And DICOM Web implementation in the Azure Healthcare APIs, we only support REST, RESTful DICOM services. There's also another DICOM transmission, which is mainly used on-prem, DICOM DMZ, but again, we are only supporting the DICOM Web in our product. And now I am switching to what we have as a solution in Azure Healthcare APIs. So we have two distinct solutions. One is the DICOM service, which is part of the Azure Healthcare APIs. It's a fully managed service. You don't need to worry about the runtime of your SQL server, your blob store, your indexing, and so on. It will be all will be handled by us. And we will be getting into GA for that product in the near future. And the other one is an open source project. It is named as Medical Imaging Server for DICOM. It is available as open source, but of course we don't provide any commitment or guarantee regarding to uptime of that service. You need to maintain your own blob store, SQL server, and so on. But of course we provide easiness such as one-click deploy so that you can easily deploy it into your local or your Azure subscription. And one key thing that I would like to highlight for those two products, we have a feature parity. So we are closely monitoring and ensuring that the whatever available features are in DICOM service are also matching the open source project. So if you would like to use open source project to test it out or to have a local development via Docker instances, you will be also getting the same features that you will get from the DICOM service. And here I'm just showing you a snapshot of the features and how they differ between DICOM services in OSS and as well as the managed service. As you can see, mainly it is the same. The major difference between open source and managed service is handling of the PHI data. And the PHI or DICOM service, we provide PHI compliance on your behalf so that neither yourself nor your customers don't need to worry about pushing PHI data into our service or into our solution. We are taking full ownership of handling your PHI data in our solution. And you are seeing just a snapshot, as I said. This feature list is continuously growing, but the key thing that I would like to highlight to you, I also brought it up earlier, we have extended query tag feature that is enabled in our service. So once you ingest or while you're ingesting the DICOM objects with the extended query tag feature, you can add additional DICOM tags into your DICOM objects that are being stored in our service, in our SQL server, that enables you to do further indexing in the data so that your cohort management or access to certain type of data per your clinic or per your research study becomes much more easy. Of course, we don't modify the DICOM object. We only register additional tag into SQL server when we are storing your DICOM object in our backend solution. And here we are having a close look into our managed service under Azure Healthcare APIs. I'm sure you have seen this workspace in the earlier call, but also would like to give you a quick overview. The workspace concept is a solution under Azure subscription where you can provision Azure Healthcare APIs so that a clinical data from your entity can sit in the same workspace, and you can definitely connect that data together with DICOM, especially with the product called DICOM Cast. So DICOM Cast, we are extracting part of the metadata from DICOM objects and then registering it into FHIR as an imaging study resource so that you have a seamless connection between your imaging data and the clinical data of a given patient. We will get into details in the coming slides, but I also wanted to highlight that it is one of the key benefits that we are providing in Azure Healthcare APIs, that you can connect your imaging data set with your clinical data set. And we can ingest multiple thousands of images per second. We allow standard-based communication with DICOM web-enabled systems. And we are managed service with runtime, middleware, and operating system support. And the key thing that I would like to highlight here, in addition to what I said, by your clinical data being in the Azure Healthcare APIs workspace, you are also having an easy integration to the advanced analytics that are provided by Azure or by Microsoft. So for example, once you synchronize your imaging data into FHIR server as an imaging study resource, you can definitely look at your imaging repo through Power BI, because Power BI has a turnkey connection to FHIR server to extract your imaging study repo, and then from there you can do, for example, cohort discovery. As well as Azure machine learning pipeline, you can definitely extract DICOM objects and push them into AML environment if you want to do further annotation and model building, and as well as model monitoring. And also briefly on the DICOM open source, it is very similar. The key difference is it is an open source project and it can be deployed as a set of Docker containers to set up your development. So if you have a development pipeline that you are working locally, open source will be your to-go solution until you bring your pipeline into maturity, and then you can definitely easily transition it into DICOM service as a managed service from your open source development pipeline. It is pretty much the same because we have the feature parity, as I brought up before. And the key component, DICOM Cast. So DICOM Cast is a resource, is a feature that enables you to connect your DICOM data of a patient to the rest of the same patient's electronic health record. It is the first cloud technology to bring DICOM metadata and healthcare data together in the FHIR spec. DICOM Cast enables the communication across the clinical and imaging data sets of a given patient, and it brings a tight integration with FHIR service and enables integration with new solutions such as a radiologist query, as it's shown in this slide, by having our service deployed. We will look a closer look at DICOM Cast, but what are the building blocks that we provide as part of the DICOM Cast is DICOM Cast, we pull the way that DICOM Cast works, in your DICOM service, as soon as new image comes into your DICOM service, we have a listener, change feed listener that detects the change in the DICOM service for the new image, and then extracts the patient ID information and checks the FHIR service. If FHIR service has the same patient ID, the imaging study metadata as a resource gets registered into FHIR service. But if there's no patient exists in FHIR service, that image came into DICOM service as an image, you can also configure the DICOM Cast to create a new patient on FHIR and register the imaging study data of that patient into FHIR service as well. And so we talked about overall what is managed service DICOM service, open source project, medical imaging server for DICOM. We talked about DICOM Cast, but also I would like to bring into your visibility what are the additional building blocks in Microsoft. So we built DICOM Service as a backend solution for healthcare space. We don't provide front-end capabilities. However, as Microsoft, we are also providing variety of building blocks to enable our customers and partners to build end-to-end solutions for medical imaging and providing better insights to caregivers, payers, and patients. And we will be revisiting some of the building blocks during the discussion of use cases. But for your highlight, we have multiple security capabilities. We ingest and persist the clinical data through Azure Healthcare APIs, but you can use Azure Data Explorer, for example, for your cohort discovery and export. You can use Power BI for cohort discovery, especially for the users who doesn't have knowledge in who doesn't have knowledge on querying language. They can use Power BI to slice and dice their imaging data and do a cohort discovery on their end. But also we have advanced analytics and intelligence pipeline that can also get seamlessly connected into our solutions, such as Azure Machine Learning Pipeline, Cognitive Search, Databricks, and so on. So I would like to zoom in a little bit on the operation of the DICOM Cast. As I said, this is just the architectural depiction of the explanation that I have given. As new image comes into DICOM service, change feed detects the new image in the service and then checks the FHIR server whether that patient exists or not. If that patient exists, it merges the metadata from DICOM server into FHIR server so that your imaging study details can sit right next to the patient clinical data. I will stop here and see if you guys have any questions. Otherwise, I will continue with the key scenarios and some use cases. Okay. On what ID is the patient merge decided? So currently DICOM Cast configured in a way that we rely on patient ID match. We look at for the patient ID in the DICOM study, and we look at the patient ID in the FHIR resources. If patient ID matches with 2, we basically enable the merge of the metadata from DICOM to FHIR. And this is just an example of the imaging study that is created based on the information that comes from the DICOM metadata. Like we capture the series, instance, and performer, and as well as some of the patient details, and bundle it as an imaging study resource and push it into FHIR based on the patient ID match. And here's a very high-level use case to show how DICOM Cast will operate in an example of an architectural depiction. So the clinical data in your EMR can be converted using the FHIR converter to be persisted in the FHIR service. With DICOM service, the medical images from your imaging modalities like CT, MRI, PET, ultrasound, X-ray, and so on, or even from your PAC systems or VNAs, can be ingested into DICOM service. Now with DICOM Cast, the metadata from DICOM images is identified and extracted to be directly connected to FHIR service. With that, DICOM metadata persists alongside the clinical data in FHIR service. And this allows for inquiries and search within end-to-end connected patient data, is once again shown on the right-hand side. So for example, if new image is ingested and there's indication that there is a follow-up action needed, the radiologist note can also be used to trigger an event for the next steps within the patient. triggered from the FHIR source, but also the images that you have ingested in medical imaging server for DICOM or DICOM service, you can also feed it to the advanced analytics or machine learning pipeline for your further studies. And here I wanted to show some of the key scenarios that we are enabling based on our service and capabilities. In both the open source and Azure managed services, we support DICOM standard APIs that are storing, searching, retrieving, and even deleting and listening to the change feed. However, I also would like to show you what those capabilities that we have in our service opens in terms of opportunities for research and life sciences, as well as in hospitals and in telemedicine. In research and life sciences, as an example, our services can be used to integrate imaging and other clinical data for analytics and research to create cohorts and close the AI ML feedback loop. In hospitals and in telemedicine, one of the primary advantages is the enablement of workflows for end-to-end connected patient data. As you know, the patient data today sits really in silos. Even within the same patient, there are a lot of data silos for that given patient that people has to do a lot of copy paste in the clinical workflow. In the operational workflow, also they need to do a lot of login, log out into different systems to be able to access end-to-end patient record. But with this connected patient data, you can improve the outcomes and decision making in clinical workflow, in operational workflow. As we are vendor agnostic, this means we can bring this value through the entire health, research, life sciences, hospital, and telemedicine ecosystem. And also, please don't limit your vision with the key scenarios that we are showing here. We are always eager to listen your scenarios and enable you as a back-end service to achieve them in your partner solutions or in your customer solutions. And if your journeys with the customers yield other areas that require enablement by us, we want to work with you to develop those solutions. For example, extended query tech was one of a most demanding additional feature that we were asked to build on top of the DICOM available tags, and it enabled further integration of our solution in a broader decision making or data discovery in a clinic area that we have customers today. So radiology use cases. To prime our discussion on the use case, I would like to start with a question for you all. Please type your estimates or feel free to unmute and speak up, but I really would like to bring up the question to us today. What is the success rate of cancer treatments today? So the answer to that question is 50%. Unfortunately, although we have a lot of advances in the pharmaceutical studies and also in the diagnosis of the patients, but still cancer is having a very low success rate. And as you know, cancer treatment is very costly, both financially and psychologically. Despite of that much expensive and tiring process, half of the patients are not getting successful results from their treatments. Therefore, there is such an important role of intelligent care in the cancer detection, treatment, and proactive studies, such as finding similar patient records for clinical decision support, giving priority on cases based on cancer detection and growth cycles, and closing feedback loop on false positive or model predictions are vital today. Currently, cancer treatment is successful in half of the patients, and connecting initial diagnostic images to digital pathology images and closing the loop between abnormality and reality behind it is one of the key enablements that can be achieved via deployment of our services in the clinical space. So we have two use cases today that I would like to show you regarding to how we can enable medical imaging in the cloud. Use case one is going to focus on how our persona can select the best path of treatment for cancer patients by leveraging end-to-end patient record. The use case 2 is about a radiologist on how they can prioritize the review of radiology and digital pathology images in the clinical workflow, which has a higher likelihood of a cancer. With that, I will start with the first use case, which is how a physician or radiologist can decide on what will be the best treatment for diagnosed patient. So we have Mary patient. She has been diagnosed for a cancer, and she is confirmed to get biopsy done with a CT scanner. And we have a radiologist who reviews her images and writes the report. But we also, as you already know, there's a requirement from National Cancer Institute in United States that every cancer case needs to be reviewed by the tumor board to decide options for treatment. And there are really only 3 treatment paths available for cancer: surgery, chemotherapy, or radiation therapy. And during the tumor board operation, the key thing that is lacking today is finding a similar patients who has gone through similar diagnosis and treatment. And according to that, the physician who makes the decision on the treatment path also need to provide that data analysis as part of his or her decision for that patient. So the key activity that will help tumor board to find similar diagnosed patients imaging, whether it is failed study or successful study, really goes through our DICOM service. What we do is, as Mary gets scanned and we have her clinical data, in Azure Healthcare APIs, both clinical data and imaging data gets ingested and persisted in our service and gets connected with DICOM Cast. And a user can use Power BI to discover the data sets that are available in the given repo of that hospital or even the hospital chain. And then basically we are opening a path for a partner to build a cohort creation and tracking opportunity to take advantage of the indexing that we provide on the back end for the given patient imaging and clinical data. So if I walk you through the steps of the clinical case in this scenario, her images are ingested into DICOM service. So a patient clinical data, imaging data, radiology imaging data, and as well as pathology data that can sit next to each other in DICOM service and in FHIR service together. And then once that data is ingested, a Power BI user interface can be created easily to talk to FHIR Azure Healthcare APIs on the background to bring the list of medications that are available in the clinical repo, and what are the available imaging studies, what are the diagnostic reports. And from here, based on the filters that you set up in the Power BI, tumor board can go ahead and search for saying that, hey, give me all the images of the patients who are women in this age range, taking that medication. And from there, a tumor board can have access to a cohort that can be exported for their further analysis to make the best path of decision regarding how they want to proceed with Mary's case. So our first case was more about on how we can slice and dice the data in a given repo so that a user can easily do a cohort discovery and export for their research, for their decision path. And the second use case is going to be about how incoming data into Azure Healthcare APIs can be coupled with the building blocks to provide a decision path on prioritizing images. So if you look at here, those are the steps in this pipeline that your images gets ingested with your clinical data, and you are using cognitive searches to search for similar images. Actually, before I dive into that, let me give you a quick brief on that. In this scenario, we have uh, radiology images and as well as digital pathology images getting digested into our Azure Healthcare APIs. But for a data scientist and data architect to be able to build a data classifier to prioritize the images based on the priority that is given by the physicians, they need to have access to data set where they have similar patterns in the medical images. For example, if they would like to prioritize the images which has a brain tumor on it, first they need to build a image classifier tool, image classifier machine learning algorithm for brain tumors. But for them to be able to build that model, they need to come up with a great pool of the data where they can annotate the data to train the model, and then they can create the model, deploy the model, and deploy the test the model, and then deploy the model on the clinical pipeline. So in this case, the way that we are constructing that pipeline, you are connecting your data sources in one repo, in one workspace, which is the Azure Healthcare APIs. You are using cognitive services tool to find similar studies based on your focus area. And you are using Azure Data Explorer to index the imaging data that returns as a result of your cognitive search. For example, you are coming up with 20,000 brain tumor images, which has the similar size of a tumor, similar size of a location, a similar location. And what you will do next, you will be using Azure Data Explorer to slice and dice the data to come up with your search parameters. So you can say that I have 20,000 images which has similar tumor size and location. And here are the detailed information such as gender, ethnicity, or age, medication history, other chronic disease history. With ADX, you can do your imaging and discovery of your data set. Once you are sure about the data set that you would like to use on your machine learning pipeline, then you will export it into AML environment. So here we have gone through this before about ingesting the data into Azure Healthcare APIs. And here you are using cognitive searches to create the pool of images that are interest to you. And then the images that are interest to you are identified. Then you are using ADX to further index the data to find exact images that fits into your category. And then once you have identified your data set that you want to train your model, you export them into Azure Machine Learning environment to perform your annotations. Once you perform your annotations and complete your data curation, then you can use same Azure Machine Learning environment to create your model and experiment your results. And once you are sure that your model is performing within the boundaries of your set, you can definitely also deploy the model as a REST endpoint in AML environment. And then from there, your data scientist and architect can take it and deploy it into your clinical environment. But here, basically, the key point that we enable the backend on onboarding data, slicing, dicing data, qualifying data, uh, creation of the data. But as a partner, we are really looking at solutions where you can build the front-end implementation so that this can be easily deployed into clinical environments. So after those two use cases, we have touched on variety of building blocks within Microsoft beyond Azure Healthcare APIs. what can be coupled with DICOM service to enable end-to-end solutions in medical imaging. And we also prepared this reference architecture depiction to demonstrate you how we can enable AI ML model consumption in the field via our current capabilities. And shown steps are modules in a given architecture with our capabilities on each of them. So you start with data resources. You are connecting those data islands into one repo by Azure Healthcare APIs. And you are connecting your imaging data with your clinical data set via DICOM Cast. And you can use creation and discovery tools that we have. For example, in open source, we have a de-identification tool that you can easily deploy into this pipeline. And then you can also use our annotation solution on the back end for labeling the images. Currently, we have 2D available, but 3D enablement is also coming up soon. And then you can train your model, deploy your model in Azure ML environment, and then basically the last mile implementation will be providing the front end to the user on how they can see the model results. They can get notifications about the drift detection in their model, and they can also integrate their pipeline for retraining and continuous learning. So by saying that, these are the key highlights that I wanted to give about our product and or other enablements that we have in Microsoft that can be coupled with our service. I would like to provide you some references. I will be also putting them into chat window. We have medical imaging server for DICOM is open source. We have ARM templates created for you to easily deploy it as a series of Docker instance, and also you can deploy it in Azure portal. And also we have instructions and documentation around DICOM service on how you can deploy it and get started by using Azure portal or by using some sample codes through CLI pipeline. I would like to stop here because this is the final slide of my presentation. We touched on those topics already, but the key thing that I also would like to highlight that we didn't talk, in addition to security and performance capabilities that we provide, we are also available in more than 25 regions globally, and that is also expanding. And I can also provide you the list of the regions that are available in Azure website if any of you are interested in that. And thank you, and I'm happy to take any open questions on your end.